category of vegetation. As you might be knowing, no two objects on the planet Earth are exactly ditto, and this property is utilized in remote sensing by way of spectral imaging. And as I go by, you will see that vegetation types, the rock types, the water, and every other thing on the Earth's surface has got a unique kind of reflectance. And this is what is caught by the sensors put on the satellites who keep imaging the Earth in its own orbit, and then trying to beam all the time the imagery which is normally available to the user. So users are not aware of most of the things which pertain to the sending a rocket to the space, which carries the payload and sensor, and of course how the data is captured, but they are more concerned about the data which is received at the Earth station in after processing, and also what actually comes to them ultimately as user through sale, distribution, or whatsoever. Now, spectral properties of the features on Earth's surface are so unique that it takes some time for a beginner to understand as to what exactly it's all about. In the backdrop, if you see the major benevolent body in the space is Sun, and Sun keeps beaming the energy towards all planets after space, including the Earth, and Earth receives only a fraction of that. And then, of course, we have the green plants, the water bodies, and the Earth's surface, which is either covered or not covered. And plants have this unique property of capturing the energy from Sun and using this energy for photosynthesis, that is for manufacturing biomass. Some biomass is of course food and the stuff that you eat every day. So it is beautiful to think that plants have developed their capacity through chlorophyll to absorb the sun's radiation and manufacture food, which is also shared by humans. And then, of course, the scientists always keep researching upon these benevolence factors, and of course the plant adaptation, and also the albedo or reflectance from the Earth's surface features, and how this entire gamut of activity in terms of energy or electromagnetic spectrum is being used by the human society as a whole. And the entire science and technology of remote sensing is based on the capturing these unique properties of reflectance of either vegetation, water, and other features on ground, so that we are able to differentiate. And differentiation naturally ends up in mapping of the features, monitoring of the features over time to find out the change, and these two things naturally help in planning and management of different natural resources, including forest resources, agriculture, crop resources, minerals, for example, water resources, and many more. So as I go by, you would come to understand as to how these features on Earth's surface behave. Let's begin with the radiation from Sun. You see, Earth receives about 1/2 billionth of the Sun's energy output. It's just a fraction, a very minute fraction of the total energy of the Sun, and that energy causes so many, actually drives so many things on the planet's surface. Surface including warming of oceans, warming of land, and the monsoon, and also a constant temperature, so that vegetation and humans can live together. And also all these things, Sun is the major force driving monsoon cycles, water cycles, and also if there is no water, there is no photosynthesis, because then water or H2O becomes a limiting factor. So if you think of the total radiation received from the Sun on the planet Earth, 34% is the one which is reflected back. 42% is used for broadening the land surface and water, and 23% is actually responsible for this water cycle. Monsoon or hydrological cycle is part. Monsoon is part of hydrological or water cycle, and wind and ocean currents. Tsunami, and tsunami is of course not triggered by the ocean, but then ocean and wind currents are surely to the tune of about 1% energy spent on them. And you see a very minute fraction of incident radiation on Earth's surface or in the ocean is captured for photosynthesis. This photosynthesis is useful to all creatures on the planet Earth, be it in the ocean or be it on Earth, be it humans or be it animals or wildlife, doesn't matter. Without photosynthesis, you can't imagine the life. And this is wonderful to see that only 0.03% of the incident radiation only is captured for photosynthesis. Imagine in tomorrow's world, if we can develop plants which are able to capture higher amount of incident radiation and convert that energy into photosynthesis, it will be a great revolution, either genetic engineering or by developing chlorophyll, which can absorb maximum or more energy than whatever so far. And if that happens, these smart plants or smart vegetation can solve actually much of the problems of the humans and of course the planet Earth. Now in this slide you try to see Earth's energy budget. Yellow is the incident radiation which is intercepted in the atmosphere before it reaches to the oceans or to the land. And these fractions I will not get into details, but then you would realize as I go by that most of the energy is received in small wavelength regions, shorter wavelength region, but after striking or absorption by the land and waters, it gets converted into something called longer wave radiation or heat. So if you see in this slide, the right side is red, left side is yellow, and in between is this orange. Orange is the absorption, yellow is the radiation or irradiance, and red is the energy which is diffused into atmosphere, and again it is intercepted by various objects like cloud, like atmosphere, like gases, like water. And so also on the left, before actually sun's radiation reaches to the planet Earth, it is intercepted by aerosols, by dust and water particles are part of aerosols, gases of all kind, and then we get, it's a kind of filtration that happens, and then finally we get energy. This energy, as I said in the earlier slide, is used in many ways by plants, by other material and features on planet Earth, and part of it is also reflected back. Imagine if this energy from sun somehow alters, all this will also change. Any change in the energy balance, either on the left or right, or in between here in the orange color, will actually totally alter the living conditions or the viability of the creatures and the plants and animals. So this is somehow is not changing as fast as many of the environmentalists have predicted. Global warming is one which is happening due to the increased level of CO2 in the atmosphere, but surely not to the extent, it is not overnight or over day, but it is in a couple of years or maybe 10, 50 or 100 years away, but then it is changing, and the heat which actually dissipates from the atmosphere is blocked on the way by the CO2 layer in the atmosphere, and therefore more and more warming back of the Earth's surface, which might have many ramifications, and like El Nino, like many other ocean currents, change in living condition, photosynthesis, comfort zone, and of course some plants dominating the others because they are more suitable for the heated environment than the cooler environments, and so on and so forth. It is said that the major loss will be to the Himalayan region, where species will try to climb the mountains, because today's glacier may be warmer by a few degrees, and on the ocean and the ice will recede over time, and therefore vegetation will climb up. It will move upwards, upwards latitudes, and the ice caps in polar regions or in Himalayan peaks will reduce. Ocean surface will rise, and all this will have an impact. Those from India will be knowing that Dwarka once upon was a land, and it was a beautiful port, Right now it is inside the ocean, about 12 kilometers from the present level, of course. So it has been rising ocean level, and it is expected to rise as per the models and predictions made by the scientists. So it's beautiful to see that, I mean, there is no other known planet which has this kind of benevolence from the sun, and the entire adaptation based on the energy that is received from the sun, evolution of life, plants and animals, and also different varieties of crops, and agricultural and forest production, and so on and so forth. This is like a big one ecosystem on planet Earth, which involves entire gamut of energy, material, and activity. This slide only shows, if you look at the radiation from sun, you can easily think of electromagnetic radiation. This radiation has got properties like it travels at the speed of light, which is about 300,000 kilometers per second in vacuum. Atmosphere is not a vacuum, and therefore it might differ slightly. It has that wavelength, which is the distance between the two successive peaks. And what are these peaks? These peaks actually denote the frequency and number of peaks that pass a point in a second is measured as hertz, and wavelength is something which is between these two peaks. As I said earlier, amplitude source is a measure of energy, and it is maximum value of the fields. And more the peaks, over time, more is the energy. You see, as I said earlier, maximum sun's radiation is received in the shorter wavelength region, and by and large, Earth behaves as a black body. I hope you know the properties of a black body. It receives, absorbs, and emits the same amount of energy. That is the nature of the true black body. Total energy received on the Earth's surface is about 6,000 degree Kelvin. Precisely, it is 5,900 something. And before it comes to us, there are various gases. For example, ozone to very less degree oxygen, water, carbon dioxide. They actually modulate, they absorb, and so the energy which reaches to us is actually a net amount of radiation which comes no doubt from sun minus modulation or interception by the molecules of carbon dioxide, water, and ozone, and ozone is at different levels. Ozone near surface, stratospheric ozone, and the ozone which actually protects from the harmful effects of UV ultraviolet light, which is again from the sun, and CO2 and H2O are the two major gaseous elements, you can say, and which modulate, and therefore when scientists, when they have to develop a sensor, actually they have to look for atmospheric windows, because it is those windows are those regions of electromagnetic spectrum which allow or do not allow scientists to develop a particular sensor for a particular purpose. So you see, much of the energy is received in shorter wavelength region, but after striking the surface and water, after absorption, it converts into longer wavelength region which dissipates. So after about 2:30 or so, the surface and the atmosphere starts is cooler, because much of the energy received in the forenoon till about 2:30 starts dissipating into atmosphere. So in the afternoon, if you have cloud, you sometimes feel heat and sultriness. That is because the outgoing long wave radiation, that is heat, is obstructed in its path by the cloud, and this actually results to the local level warming, and surely clouds intercept both incoming and outgoing radiation, as you know. This slide precisely shows the atmospheric windows. By windows I have already explained. These are the wavelength regions where we have freedom to design our sensors. So you see, from roughly 0 to 2, we have quite a bit of width wherein we have freedom, and many of our sensors, they are designed to operate in this wavelength region. Here you see CO2 nearly absorbs all incident radiation, and CO2 has got many drops, many values, 1, 2, and of course the water is one of the widest, is between 6 and 8. Then again here 10, this is ozone, and from about 13 to about, less than 18, you see this major absorption by CO2. So when we work, when instrument making companies work on the CO2 measurements, they actually also work on this principle, because CO2 modulates incident radiation, so they use infrared to gauge the CO2, and of course those which measure water vapors also work on almost similar principle. So by this diagram, I need to emphasize that we have fewer opportunities, not that the entire spectrum, electromagnetic spectrum can be used, but we should look for the atmospheric windows or avenues which help us in focusing on those areas for developing the sensors for various purposes. Now, if you look at this, when we talk of visible region in which our eyes operate, you might be knowing the eyes are one of the best sensors available with the humans, and we keep on doing the sensing all the time, day and night, except sleep time. If you think of only this big region, it's very narrow, from 400 to 700 nanometer, but we can have sensors right from X-rays, like in medical technology, ultraviolet, near infrared, middle infrared, and of course the far infrared. And then far infrared is the one which is called as heat. Then of course microwave, which is the region from about 1 millimeter to 1 meter, and then we have long waves called radio waves, and each one of them have got their own wavelengths, frequencies, and amplitude, and so on and so forth. So whenever we try to develop a sensor, we focus on this property of reflective property of the radiation, then of course absorptive properties, and then the nature, wavelength, and then the frequency, and all that matters a lot. So people who deal with remote sensing, image interpretation, and mapping, they should know precisely as to what wavelength are they concerned with, what is their job to be done, and which region or which band is best suitable for their purpose for which they are making use of satellite imagery. In a nutshell, I would like to say that we made a very tiny portion of electromagnetic spectrum for remote sensing to say, although it's possible. We already have microwave sensors, both active and passive, and we have now laser which operates around 1 micron. Radio waves are being used for the broadcast radio transistors. Microwaves are used for the TV transmission, satellite tracking, and telecommand systems, and so on and so forth. So each one has got their own use, and we should be aware as to what bandwidth or what portion of electromagnetic spectrum precisely is being used by a sensor, because this enables you to know whether X product, let's say satellite imagery, is useful for one purpose or the other. That makes you knowledgeable about the basic property of basic part of electromagnetic spectrum which is being utilized. Here is the more detailed thing. This is of course the microwave region, then we have infrared region, we have ultraviolet region, X-rays, we have cosmic rays, and so on and so forth. And as you go by, you have radio waves which are a few meters long. And these details I will not get into, but it's precise to say that eyes operate in a very narrow domain compared to the eyes of the most of the animals of the cat family, the owls, etc. Human's eye operate in a very limited region of electromagnetic spectrum, but sensors can be developed for a variety of reasons of electromagnetic spectrum, and they are there already used for specific purposes, either for medical imaging or for remote sensing, for example. Up to here, and or for broadcasting and relays and controls and so on and so forth. So it is interesting to see that we are making use of the electromagnetic spectrum, which is again a benevolence of the sun, and without that perhaps we could have been a little constrained either in communication, in remote sensing, in medical imaging, and all these radio relays, broadcasts, and so on and so forth. This I will skip because this is a repeat of that, and the basic player when it comes to vegetation, and so also in each discipline like soil and rocks and water. There are players, for example, those who are interested in water are supposed to focus in the areas like blue and green part of electromagnetic spectrum, and up to middle infrared, because beyond that water is completely absorbed, so there is no point in using higher wavelength reason for sensing of water bodies and or monitoring. In case of vegetation, leaf is the major player because it contains chlorophyll. Chlorophyll A and B, xanthophyll and other pigments actually, and then the intercellular spaces and the moisture inside, and the entire structure or you can architecture inside modulates the incident energy from the sun. You notice here that green plants look green because they reflect green to the tune of about 17 to 18%. Imagine if we have plants which reflect 50%, they will be simply super. And the rate of photosynthesis, for example, are for example, plants which absorb the entire incident, red region, electromagnetic spectrum or energy, they could produce large amounts of biomass and perhaps do away with a lot of things which are related to nutrition, food, and biomass energy. Near infrared, as you notice, with the wider, thicker arrow, is modulated by plant leaf, but it is not dependent on chlorophyll, but structured into cellular spaces as such. And you see, cell structure is important. Surface properties of the leaf are important. A leaf with a reflective surface is a lot better than the leaf whose top surface is actually has got bristles or hair. Chlorophyll content, of course, you have the total quantity or density of chlorophyll per unit area, and water content inside the leaf influences reflectance significantly. Invisible and near infrared. In a nutshell, I would like to tell you that if a plant is healthy, everything will be to the tune it is expected inside a leaf, because leaf is a marker or indicator of the health, a number of leaves, leaf area index, and so on and so forth. Now, anything that happens to a plant, let's say less watering or dry season or drought, or for example, lack of nutrients or less nutrients, anything are damaged by anything else, or extra heating and no watering, all those will actually modulate these things, cell structure and therefore surface properties as well, and the chlorophyll content, and which ultimately will be reflected like the way I have shown here. And these leaves will be different than a healthy plant, and therefore we are able to make out the diseases, the insect infestation in forest areas, the plantations, and also in some cases the necrosis and distress vegetation because of n number of factors. Now, this is a master diagram. Here it is vegetation reflectance, but in the other slides you will see also reflectance of the other ground surface features. Look at the top. The reflectance in visible to near infrared region is mainly due to the leaf and chlorophyll A and B, xanthophyll, and many more. And then, of course, in near infrared, largely it is because of cell structure, which is an intercellular spaces, and also moisture which is inside the leaf. And you will see a mild, not so steep peak, then the absorption or trough, then very high reflection in near infrared region, and of course near about 1.4 and 1.9, there are two troughs which is related to absorption of water. So those who are interested in duration or potential evapotranspiration, they are advised to use this portion of the electromagnetic spectrum or the product generated or imagery generated these bands, middle infrared. Normally when you make use of green reflectance, which is about 17–18%, and red absorption and near-infrared reflectance, which are the three wavelength bands which are used for making false color composite, which is called a standard false color composite. It gives you maximum contrast. Why? Because there are contrasting characteristics over here in terms of reflectance, all right? And this false composite is by and large said to be good for all kinds of users, although not exactly to all people, but then surely by and large, yes. And imagine if you can engineer plants of tomorrow which have more chlorophyll and therefore more reflection, and this stuff will be deeper, more absorption means more photosynthetic production or biomass, fruit or vegetable or pulses production, and steeper this slope, healthier is the plant. Many scientists are working on the red edge and making use of it to gauge the health of the crop, the health of the plantation, or health of the plant. And this of the blue wavelength and the creating an illusion called sky. We avoid blue because the image contrast will not be good if you use blue, but in normal camera photography you cannot avoid blue. You have to take, because it is close range photography, blue, green and red, and then there is nothing called chlorophyll reflection or absorption. It's only simple RGB, only intensity matters. Now here you see an additional, two additional reflectance properties in terms of dry bare soil and of course the reflectance from the water, and you see it is something at 0.75 micron, because after this it is completely absorbed. So therefore those who are interested in water, they use satellite imagery which has been acquired using this portion of electromagnetic spectrum, while vegetation and crop specialists make use of imagery which has been acquired using at least green band. And if your other band is not harmful, which I don't mean to say, but surely green reflectance, red absorption, and high near-infrared reflectance. Of course, soil doesn't have pigments, soil doesn't carry photosynthesis carry on, and of course soil also has got some soil has got water or moisture, and you can see these peaks which are correlatable, and it is entirely different, just like a freight curve. And these properties, those people who understand as to how a particular feature on ground in terms of spectral reflectance behaves, they will perhaps be better interpreter of the satellite imagery. This is what I mean to convey. Here you can see some more features like deep water and shallow water. As you must be knowing, even deep water, if it is mixed with the silt or sediment, appears shallow, and sometimes it's a dilemma for hydrologists to make out, the total quantity of water simply, from the reflectance value alone. So they use models, they many other things which is not my subject area. And you see among the soils, the silty clay soil and the muck soil, they also behave differently because of the inherent properties. And of course the green leaf, you see, as usual I have shown earlier. And the beautiful thing which you did not see earlier is here this water which is deep or water which is shallow. Sometimes deep water appears shallow and will have this property because it has a whole lot of sediment load, especially during rainy season anywhere in the world. Here you can see a spectral reflectance of healthy and stressed vegetation. Stress could be because of less availability of water, less availability of nutrients, higher temperatures. Even humans can act to vegetation stress, and this will modulate the quantum of the chlorophyll. This will also modify or or perhaps alter the leaf properties like leaf structure, and that in the course of time actually amounts to leaf stress of some kind, and this leaf stress is actually reflected if you have this kind of curves from the vegetation. Look at the green one; it shows healthy green vegetation. The next one is stressed vegetation. You see here, all things are happening. Green reflectance is not too much affected, slightly, but then photosynthesis, chlorophyll is less, and therefore stress vegetation subsequently is shallower. All right, and then here you see infrared. Here you see the steep slope, but subsequently the slope is not so steep, and the peak is not like healthy vegetation, it is less and less, but basic properties remain. Water absorption here is same, although you can see here there is a whole lot of change in the reflectance. It is increased because water is not there in the leaves, and here again. So any stress that amounts to any stress for vegetation or any property change in other features on Earth's surface will actually be reflected in this spectral reflectance diagram, and this diagram would of course tell the interpreter the properties of the feature, and when he interprets the imagery, he will take care. Normally he will make use of this knowledge in the interpretation. Here is the case from the diseased vegetation. Of course, you can see the healthy one first, and then you can see the green one soon after the disease has set in, and of course the last one long after the disease has set in, and you see the green reflectance has disappeared. Red absorption for photosynthesis is no more there, and the leaf structure is totally modified because plant or vegetation is diseased. So if you have healthy and diseased vegetation side by side in any satellite imagery, it is most likely that you will be able to differentiate diseased vegetation from healthy, because chlorophyll has got changed, and since chlorophyll quantity and condition change, the photosynthesis is not there, and then the overall cell structure is also affected. So from normal curve, it has finally resulted. People often ask me how to detect disease using remote sensing, and this diagram is just one line explanation for that. Diseases of all kinds modulate the chlorophyll content and the cell structure, and therefore the change in the reflectance pattern of the vegetation, which provides contrast from healthy one, and that is the way how we identify diseased vegetation. And if you think of the different vegetation on planet Earth, there are many types. Here I have only 6 of them, and they are very close by, because these vegetation and forest types are very close to each other. But then you see, if you have to take this color, which is of mature oil palm, and think of this one, which is young oil palm, there is very high contrast. Because young oil palm or young trees, young plantations are full of chlorophyll, per unit area chlorophyll density is very high, so you can see their reflectance pattern is different. This is the reason as to why we are able to differentiate different vegetation types. For example, this will be mature palm will not have overlapping signature with the forest area, and forest area will not have overlapping signature with the banana, and so on and so forth. But surely you will have some problem between this and this, and more so between this and this, more so between this and this and this. And if they are far apart, maybe this from this, or this from this, or this from this, then you can think of having better contrast in vegetation types, and therefore ease of interpretation, mapping, and monitoring. Now here you see the birch and you see fir, and you see pine and grass, of course. It seems here the grass has got maximum chlorophyll per unit area density, you can call it, and see a typical curve, but the other coniferous species are not having chlorophyll to that extent, and therefore lower level, although the basic curve is same, but then the peak attained by the grass is much more than for birch and pine and for. And therefore, if you have this kind of situation in field where grass, birch and pine and firs at the same place, I can say with confidence that this satellite imagery will have maximum contrast. And this contrast means higher accuracy of mapping, better monitoring, and so on. This figure shows the reflectance and vegetation growth stage relationship. Here is the moist soil, here is the dry soil, and here is the surface of the soil without vegetation, and after it vegetation develops and canopy is there, then there is a whole amount of change in the reflectance. Vegetated area generally near infrared will have more higher reflectance because of large leaf area index compared to a surface which is bare soil. And the diagram conveys as to when vegetation develops, everything changes. The albedo of the earth's surface changes. Land is covered with vegetation. Vegetation has got chlorophyll, moisture, etc., and it develops a canopy. Canopy, then, if it is closed canopy, then canopy becomes the surface. The soil is masked, and this is where entirely in a different way than the bare soil. Now, let us see the reflectance of common land features. Could be rocks, could be minerals, could be water or any other things. And you see that if I have to plot all those, I mean, in this graph it will be very clumsy, but you can see that geological features and plant features, soil, everything has got its own characteristic reflectance pattern, which we always say that each feature on the Earth's surface is unique, and therefore we are able to identify, although nobody has said so far that yes, because of this property we can identify 100% all Earth's surface features. Why? Because there are overlapping signatures, and this creates a problem in all kinds of classification techniques, algorithms, and so on and so forth. So, but then yes, as features, they have these unique properties in these spectral regions, and the scientists all over the world are trying to identify them based upon this property, map them, because many of them are high economic importance and useful to humans and animal life. Now, this is perhaps the last slide that I have, normalized difference vegetation index. I hope many of you are aware that we make use of R and near infrared to create a new index which is indicative of the greenness, the robustness or health of vegetation, and this can be further density sliced, and some people density sliced to make the vegetation cover or crop cover or forest cover from this. Here you can see the FCC, this is basically from the red band, near infrared band, and from that you can generate a gray image. NDVI values, when you generate through NDVI, it varies from -1 to +1. You can have the density, slicing and assign a color as you wish, or you can make a vegetation cover density map, etc., which is useful in more than one way. And NDVI is the most widely used vegetation index globally, although there are more than 275 vegetation indices throughout. Indices are a product of reflective or reflectance property of the vegetation. So also in many other science disciplines, they have their own indices to be able to identify the features of particular interest and able to map and monitor. I have some sample images for you, and see this image, I will not say which area or what. This area has got a whole lot of shades of red. One thing is that red is particularly associated with the green live vegetation. So one clue that you get from this is that it must be vegetation. it must be green, and it is also, this is different, for example, from this, so it must be a different vegetation. So also, for example, this one is different from this or this, so it must be different. And scientist, when he sits on for interpretation, first he goes to the ground, try to identify the things on ground, then looks at the imagery. Mostly in optical data, ground and imagery, they are one-to-one correlated, so easy to interpret, but not so good in microwave data or even LiDAR data for that matter. Because LiDAR and microwave depend upon the vegetation structure and composition rather than reflective properties of the vegetation. Naturally, a question arises, can we interpret all kinds of vegetation? Yes, this is a planted area, and this is a unique plantation, and therefore we are getting very high contrasting. This is sal plantation, pine plantation, this is the mango and the lychee plantation, this is champa plantation, you can see bamboo, you can also see the poplar nursery and the lawns, and the building and the mango grove, a couple of trees planted together, and of course a variety of the trees that are in the campus of Forest Research Institute, and you can also see eucalypt, how they look, and if this is eucalyptus, you can easily assume this all should be eucalyptus, and it is true. You can see a sago, teak, and if you know this is teak, you can also know this might be teak, and this is true. Although teak with some other growth, this is also teak, and this is also teak. That is why when you use remote sensing, and if you know some plant for sure by ground truth and also an image, then you economize in the survey and spend less money by going to every patch normally, otherwise you need. Even with one patch, you can make out a lot of things about the other patch of some kind. For example, if you know that this is pine, cheap pine, then the next question is it also cheap pine, and the answer is yes. So there is economy, there is accuracy, and surely I would say that the spectral properties of Earth's surface feature greatly captured by the sensors and converted into image enable us to be able to monitor, map and monitor and assess quantity, spread, distribution, and so on and so forth. Other things I will not get into detail, but look at this forest plantation and agricultural crop, very high contrast. And this again is in contrast with crop, eucalyptus for example, here is in high contrast with the crop, and harvested, forest area, mostly it was eucalyptus. If you know this is eucalyptus, then surely this and this all should be eucalyptus. So this is how there is economy in mapping using remote sensing, and scale plays a large role. See, this is a larger scale than this one. Here you see there is also a small tiny dots only, but here you can see these are big houses. You can even count houses going to without going to this area. So that kind of capability to exist, and we have also high resolution data. And we have some features like shifting cultivation in Northeast India, Orissa, Chhattisgarh, and other states of India. And you see the blue one here is just burnt, ready for debbling of the seeds and cultivation. And these are all different shades of red, secondary forest which has come after shifting cultivation, and the original forest which was there in the entire area of now used by shifting agriculturists. There is no correct biosphere. This is Tura in western Meghalaya, and all this is secondary vegetation, the burnt area ready for cultivation, and the original vegetation, which is very dense and tropical, almost tropical rainforest type, tropical with evergreen, forest type, which is now protected. So again, why do we see different shades of red? Why do we see different shades of blue? Why do we see different shades of Earth's surface over here, for example, and here? This is all because these cover types or these features have got their unique reflective properties in different wavelength regions, which are used for making false color composite or imagery. Then this is tsunami, and you can see if you are a biologist, for example, interested in mangroves, then you can focus that all these red areas, They have the mangrove forest, the Trinket Island in Andaman Nicobar Islands, so also over here. And these are uplands where salt water and fresh water interface is not there, and therefore these areas don't have mangrove forest. In 2004, when the tsunami came, actually this island got cut into two due to the strong waves, and now this is Trinket 1 and this is Trinket 2. But the beauty over here, you can see cloud, you can see cloud shadow, you can see shadow waters, you can see part of land, which are submerged very, which have got water, vegetation underneath. All the land has been washed away, and you can see the vegetation which is not underwater, and you can see human enterprises like agriculture over here and so on and so forth. So beauty because of reflective properties of the vegetation, and otherwise you will not be able to see the imagery of this high quality. Thank you very much.